Today we're going to be looking at a 1.7 times 10 to the minus third solution of acetic acid. And our goal today is to determine the pH of this solution. So you're thinking, okay, no problem, Rachel, get to the board and do it. So I'm going to go ahead and write down that we have CH3COOH, acetic acid, at a concentration of 1.7 times 10 to the minus third molar. Now that we know that, can't we just go ahead and assume, like we did before, that the hydrogen ion concentration is then equal to 1.7 times 10 to the minus third molar as well. And from there, why not just plug in to our good, trustworthy equation for pH being equal to negative the log of the hydrogen ion concentration. And we'll plug then in 1.7 times 10 to the minus 3 molar into that equation. So our pH equal to negative log of 1.7 times 10 to the minus third. And this is going to equal, okay, now everybody has their calculators, I hope. I'm just going to run and grab my calculator. Hey, got it, 2.76955. Okay, we're not going to retain all of those significant digits. So let's say that our pH should be equal to 2.8. So let's just write that down. A pH of 2.8. Okay, so I brought with me some sweet little pH paper, and we're going to spec this out. So pH paper, very handy. We're just going to verify our calculation. Oops, I just threw pH paper all over the place. Oh well, we need some anyway, right? So let's do a quick dip and find out if we can verify our pH. So, quick dip. I feel like that some days too. Okay, at least a quick dip. Okay, so let's check this out now. I'm going to bring this pH paper near to you, and we're going to look at this, and ooh, booger. Not so good. We're not verifying too well, are we? This looks like a pH of roughly 4 to me. What's going on? What's happening here? I have a feeling that a few of you are yelling at the screen, saying, wait, hold on, a long time ago, stop making incorrect assumptions, because I made an assumption here. I assumed that the concentration of acetic acid is equal to the concentration of hydrogen ion. I can't do that because acetic acid is not like hydrochloric acid. It is not a strong acid. In fact, it's a weak acid. So we can't make this assumption that hydrogen ion concentration equals acetic acid concentration. Why? Because dissociation is incomplete.
Let's dig deeper into this notion that weak acids do not dissociate completely in aqueous solution. And we'll go on with our acetic acid or vinegar dissociation, CH3COOH. We're using the simplified equation, dissociates to CH3COO minus conjugate base plus H plus. We can write an acid dissociation constant for this, Ka, is equal to products CH3COO minus times H plus over CH3COOH. Now, your book simplifies this to just being, they get rid of the A. So I will often use Ka, but they use K. So then if we want to look at a simpler value, pKa is employed. So just in the same way that we use pH, for simplicity, we can use pK or pKa is being equal to negative the log of the Ka. And of course, this enables us to deal with values that are less cumbersome. Now, Ka is experimentally determined, and so in fact, we know this value for acetic acid. The Ka is equal to 1.76 times 10 to the negative fifth molar. And so if we plug in to get pKa, we find that that is equal to negative the log 1.76 times 10 to the minus fifth, and that pKa or pK is going to be equal to 4.8. It's like, cool, that's a less cumbersome number, but what does it really mean to us? Well, I mentioned that these are experimentally determined, and so if we're looking at a weak acid, what we recognize is that its likelihood of giving up its acidic proton is going to be very much dictated by the pH of the solution. So these values are experimentally determined by titration experiments in which strong base is added to the solution of weak acid, and the more base that is present, the more acidic proton is going to be given up.
So let's look at what we have here. We've got a ring stand, and attached to this is a clamp that comes out and around a long skinny burette, and this burette would house the strong base. And from this you could turn the little knob on the burette and allow dropwise the equivalence of sodium hydroxide to enter into the beaker down here, which contains the weak acid. So essentially you're adding the equivalence of sodium hydroxide and monitoring then the changes in pH within the solution of acetic acid. So notice here my cheesy depiction of a pH meter with its electrode coming in and reading the pH in the acetic acid solution. So what we're going to watch in this animation is as equivalents of strong base are added to the sodium, as equivalents of sodium hydroxide are added to the weak acid, we're going to watch as the pH changes, and we're going to see how we could monitor then the complete titration of the acetic acid as it goes from the fully protonated to the fully deprotonated form. And after we finish this, we'll look at how you would graph that information and take away messages from that. So we'll go ahead and keep our eyes trained on both the addition of the strong base to the weak acid, as well as keep your eyes on the pH meter and watch how the pH changes. And we'll notice it with equivalents of sodium hydroxide. At first, the changes in pH are very drastic. But then, as we start to get to this sort of center region or midpoint of the titration, you're going to watch that the changes in pH are much less drastic. So let's see this happening and keep an eye on all that's occurring. It's a little hard to watch everything at once, so if we need to do it again, we can. So here we go, the strong base being added to the weak acid, it's getting stirred with a stir bar, watching the pH meter change, and here towards the midpoint of titration, it changes slowly, and then at the very end, it changes much more rapidly. So this is how you would experimentally go ahead and determine the pKa, and we'll now look at how we would graph that and actually visually see the pKa.
So we can actually take a look and simplify this, I hope, a little as we go. If we make a graph that could be experimentally determined in which pH is given on the y-axis, and either the equivalence of strong base that is OH minus, or we could look at this as also being the hydrogen ions dissociated per molecule of our weak acid. So let's start with this notion that the more base we add, the higher the pH gets. So we start over here at very, very low pHs until finally we get up to higher pHs. So if I just note that this is a pH of 1 and 2, 3, 4, 5, and we just keep climbing up, neutral, 8, 9, 10, 11, 12, 13, and finally at the top here, 14. As more base is added, so the more sodium hydroxide that is added, and we look at this in equivalence, so we would just tend to see this as 0.5 and this as 1. And in a minute I'll explain how this also can be hydrogen ions dissociated from the weak acid. So if we're at very, very, very low pH, that is, we're way down at a pH of 0, then we recognize that a weak acid will maintain its acidic proton. So looking at our vinegar, our acetic acid, we can recognize that this is the acidic proton. At pHs of 0, that acidic proton will be retained by the acetic acid. However, the more and more basic it becomes, the more that acid is going to give up its acidic proton. So at pH of 14, it will have completely given up that acidic proton, and the predominant species in existence will be the conjugate base. So what we can recognize is that we can draw a titration curve that shows the species that exists at particular pHs. So at a very, very low pH, we know that at these pHs that are below the pKa value for this acid, we can recognize that the acetic acid will maintain its acidic proton. So looking here on our graph, if we note this as about 4.8, then what we can say is that below pHs of 4.8 here, that the protonated species CH3COOH will predominate. And we can draw this in the form of a curve. So as we raise the pH and eventually add 0.5 equivalents of base, in all of these pHs below the pKa, then here CH3COOH predominates. Now notice that as we reach the pKa value for acetic acid, we see this region in which the pH changes occur very, very slowly. This plateau that occurs right here, or termed the midpoint, is a region where the solution is resisting changes to the pH. That is, it's acting in this region the way that a buffer acts. It acts as a buffer. Now, as we add more and more base, we start to see that inflection point change, and the species that predominates at pHs above the pKa is the conjugate base, CH3COO minus. Now, at the inflection point, or the midpoint, here at a pH of 4.8, the pKa, the concentration of CH3COOH is equal to the concentration of CH3COO minus. That is, the acid conjugate base are present, acid and its conjugate base are present in equal concentrations at the pKa. So by adding more and more base, we're titrating off the acidic proton. So what we can recognize is that the stronger the acid, the more pHs over which it is deprotonated. Notice that for acetic acid, it is present in the predominantly deprotonated form over the pHs 4.8 through 14. That's a large region of the pH scale. We know for hydrochloric acid, remember talking about it as a strong acid, it's going to be deprotonated over the entirety of that pH scale, a stronger acid. Now, if we make up a fictional acid that I'll draw in with a different curve, we could recognize this fictional acid as potentially having a pKa or pK of equal to 2.2. Let's pretend, and our fictional acid here, its inflection or midpoint will occur at 2.2. So as we add equivalence of strong base, and we hit the midpoint, and that resists the pH change, and then as we add the full equivalence, it completely titrates off that acidic proton. So you can see why ions dissociated per molecule is also a good measure for this x-axis. So at this point, what we see for our fictional acid, let's call it HA. Just recognizing that in this case A stands for acid and H is the acidic proton, so as it dissociates, then we get A minus plus H plus. So we recognize that at this midpoint, A minus is present in equal concentration to HA. And of course, now at pHs of less than 2.2, HA is going to predominate. At pHs of greater than 2.2, which is a big range of the pH scale, we know that the A minus is going to predominate. So in here, A minus predominates. Neat. So everywhere above 2.2. So that's a stronger acid. So this can allow us to derive an equation that allows us to calculate the exact concentrations of A minus and HA at any given pH. This equation is called the Henderson-Hasselbalch equation. As we ready to derive the Henderson-Hasselbalch equation, it's helpful to have our titration curve reminding us that the pKa for this weak acid HA is 2.2. So at pHs above 2.2, A minus, the deprotonated species predominates, whereas at pHs of less than 2.2, we know that the protonated species HA predominates. And then, of course, right at the pKa, we know that HA and A minus are present in equal concentrations. But it's really great if we can think about getting an expression, a mathematical expression, that could help us to better understand the ways in which the ratios of the conjugate base and acid will relate to pH. So say, for example, maybe we put in a certain molar amount of A minus and a certain molar amount of HA, and we want to know, well, what would be the pH? Oh, so can we derive an expression knowing that this is the dissociation expression for HA? If we want to look at an equation that would allow us to relate Ka and pH, this is something we can do, right? We know that Ka is equal to A minus times H plus, the numerator, and then divided by concentration of HA in the denominator. And now we can go ahead and solve for H plus because we want an expression that will allow us to understand pH. So if we solve for H plus, that's equal to Ka times HA divided by A minus. And we now can take the negative log of both sides of the equation. And then just using rules of log, the negative log would be the log of the reciprocal. And this starts to give us something that looks really familiar. Negative log of H plus, negative log of Ka, pH, and pKa, or pK, plus the log of A minus over HA. And this is it, the Henderson-Hasselbalch equation. And this is incredibly useful when it comes to determining the pH that we would have in a solution where we had a given amount of the conjugate base and the acid. So today in class, we're going to do a lot of practice with this, and we're going to not only utilize the Henderson-Hasselbalch equation, but we're also going to redraw some titration curves for weak acids, but we're going to even delve into drawing the titration curves for polyprotic acid. Now there's where things start to get really interesting.